Great, thanks, Andreas. So today I'm going to be talking about cache coherence in gem5 and modeling cache coherence with Ruby. And this is part of my ongoing, incredibly slow work of writing this Learning Gem5 book. This is one of the longer sections that I finally found time to get to. So to quickly go through a little bit of history and why there's this separation between the classic memory and Ruby is initially Gem5 was the M5 project at Michigan and GEMS at Wisconsin. And M5 had really great support for CPU models, this master-slave port interface, and had a cache model with it. And then GEMS, on the other hand, had Ruby and network simulation and other GEMS like Garnet came into this GEMS interface, but it didn't really have, it would use SIMX on the back end for execution. So when SIMX licenses got harder to get, we moved and migrated Ruby into Gem5. So this is kind of why these two memory systems are completely separate. And we'll see a little bit about how they interact as we go through. So like I said, this is part of this book called Learning Gem5. There's some other talks that I've given which cover the first two parts between getting started with it and creating some simple SIB objects in the second part. Here I'm going to talk about Ruby. There's also some information on full system simulation, and there's always more coming whenever I get time to write more. Okay, so this is an outline of what I'm going to talk about today. I'm going to give a little bit of overview of what Ruby is and how Ruby works and how Ruby fits into Gem5. Then I'm going to go dive into some amount of detail about how you write a cache coherence controller. So for a particular cache, the L1 cache, how do you actually go through and write this state machine logic that implements cache coherence? Then I'm going to talk about configuring Ruby and a mishmash of a few other things as well. Okay, so at the high level, how does Ruby work and what is the design of Ruby? So there's some things in the system which are going to be injecting traffic into the memory system. So these would be the master controllers in the TLM parlance. So things like CPUs, DMA controllers, other things, you can have GPUs or other accelerators as well. Then there's Ruby, which from the perspective of Gem5 is really just a big black box. You just have these things just dump requests into Ruby. So all these requests go into Ruby and then something happens inside. And we'll look at that in a minute. And then on the other side of Ruby, you have the memory system, the memory controllers. So you have CPUs injecting traffic in, traffic comes out of Ruby and goes into the memory controllers. And everything that happens in this Ruby box is completely separate from really the rest of the way the Gem5 system looks. And going into and out of Ruby are just the classic Gem5 ports, the master and slave ports that are used in the classic caches. And I'll talk a little bit about how you get stuff in and out and how that interface is implemented towards the end. Now, if we dive down and look at what's inside of Ruby, again, it's kind of like this black box idea. You have all these different controllers, so things like your L1 cache controller, your L2 controller, directory controllers, DMA controllers, whatever controllers you're going to have in your cache coherence protocol. You have different implementations for all these things. And then you have, again, kind of this like black box interconnect. And Tushar, after the break, will be talking in more detail about how this interconnect works. But all these controllers really just dump requests into this network. Then the network figures out the way to route things and get things from controller to controller. And then you receive messages out of the network from these controllers. So Ruby is really made up of three major components. You have all these different controller modules that you create. And these are written in a domain-specific language, SLICC, which we'll talk about in a minute. You have the topology of these controllers, which is how they're connected to one another. And then you have the network model, so how you're modeling packets going through the network of this on-chip interconnect. And Tushar is going to talk in more detail about both of those in the coming talk. And one of the things that I think confuses people some about getting started with Ruby is it's really designed for flexibility. It's not designed to be easy to use or easy to configure or easy in any sense at all. but it's designed so you can take whatever protocol you want and mash it up with any topology. Take any network model and mash that up with any protocol. So that way you can really easily get a very wide range of different kind of configurations and in detail model all these different things. And each one of these things has multiple different models which are higher and lower fidelity as well. I'm also going to talk a little bit about the interface between the classic cache ports and Ruby as well. Okay, so let's dive into how you create one of these controller models. And this is really where I'm going to spend most of the time talking today. So as I mentioned, they're implemented in this language called SLICC. And so the actual code for the controllers is generated via the SLICC compiler. SLICC is a source-to-source compiler that takes SLICC code and generates Python and C++ code. Then that Python and C++ code is compiled into gem5 when you run scans. So the original purpose of SLICC, and if you have ever, how many people have looked at a SLICC protocol? A few. How many people have written one? Oh, wow, okay, cool. So if you've written one, there's some really weird things about it. And one of the reasons for this is the original purpose of SLICC, when the original authors came up with it in the late 90s, I believe, was just to generate these state machine tables. So they were doing a lot of cache coherence work and wanted to generate these tables. This is from a book that came out a few years ago by Dan Soren, which I think I saw around here somewhere, Mark Hill and David Wood. And they found it was a real pain to generate these tables, which describe cache coherence protocols. So they created SLICC, which would take a state machine definition and generate an HTML table. And so you can actually still do this today. And so this is that same protocol, but output with SLICC. And you notice the biggest difference is this has many more details, because when you actually implement a protocol, it has a lot of details. So this is still one of the big ways you can use SLICC, and it still does this. Okay, so as I go through this example, I just want to point out this is a really quick overview. The example is actually a few thousand lines of code, which I'm not going to go through today. But I did put it all online, so you can check out in the book. I quickly went through and wrote all this up, and so it has details of how you implement this coherence protocol. It's based on an MSI protocol, directory protocol from this book, which if you want to learn more about coherence, this is a really great resource for learning about cache coherence. Okay, so when you create these state machines, you create a SLICC state machine file. And so the first thing you do is you declare this state machine. So in this case, we're declaring a machine. Yeah, that doesn't really work. And the machine type is L1 cache. And so the L1 cache is just the name of the state machine that we're creating. And you can also pass a number of different parameters to this. And so when the SLICC compiler sees this file, you run SLICC on this file, it generates a number of generated files, one of which is L1 cache controller.py. So this L1 cache came from the name that we gave the controller previously. And in this file is just the normal SIM-object declaration file. So it's just like every other SIM-object in the system. It has this py file that has parameters. Whatever you declared as a parameter in the state machine file shows up as just a normal gem5 parameter. And it's just a SIM-object. You can configure it from Python the same way as everything else. It also generates the actual code for implementing the SIM-object. It happens to inherit from abstract controller, which is relatively important if you're trying to figure out how things fit together. And it's just, again, this is just a SIM-object. And then it also generates a bunch of other files, some of which are determined by how you implemented the state machine, some of which are always generated. But one important point here is that you should never modify these generated files. You can go and look at all the files. They're in the build directory. You can look and see how the C++ code is actually implemented, but you shouldn't modify them. If you want to change those files, you should change your SLICC code. I've actually heard stories of people going in and mucking around in these generated files, and it's very error-prone, and who knows what they were actually modeling in the end. All right, so go through a quick outline of what we expect to see in these state machine files. The first is parameters, and these parameters also often include a cache memory, and the cache memory is where the data for the cache is stored. So the state machine file is really just that. It's a file that describes the state machine or the cache controller. All the data is in this other separate object, which is a parameter. You have parameters which are message buffers, which is what you use to send things into and receive things from the network. Then you declare what kind of states you have in the state machine. The events that you have will trigger in the state machine. There are many other structures and functions as well, many of which you can just copy-paste from other state machines. Then there's the important parts, which is what events do you trigger when you receive messages, the actions that you perform as you're transitioning from one state to another, and then the actual transitions, which say when you're in a particular state and you get an event, what state do you go to and what actions do you trigger? So the way this all kind of hooks together is you receive a message from a message buffer, and it goes to this import. The import select based on the event that you want to trigger, looks at the transitions, and looks at the current state of the cache block, what event you're triggering, and then it performs actions. And these actions can be something like sending a message or updating data in the cache, or something like sending a message into the network. And that's how all these components in this file interact. So to briefly talk about some of these components, there's the cache memory, and this is where the actual data in the cache is stored. And again, one of the important things about, or well, one of the main designs in Ruby is to be really flexible. So even something like the cache entry, what you're storing in this cache memory, is completely up to you. As you're writing your state machine file, you can put anything into this entry structure. Usually you put data and the state that you're in, but you could put anything else as well. Things like, say, tokens for token coherence to count the number of tokens that you have. Anything can go in this. And so it's very flexible, but also can be confusing. One important caveat, which is a really easy mistake to make, is whenever you access something on the cache memory, like a real access, you need to call set MRU. Otherwise, your replacement policies just won't work. Again, replacement policies are flexible. You can plug in and out replacement policies, but you have to go through this extra pain of making sure they're working. Next is the message buffers. I have to admit these are really confusing, especially coming from normal gem5 land. You have two message buffers and from message buffers instead of master ports and slave ports. And there's a bunch of different functions you can perform on these message buffers. The bottom two are particularly important. These are used whenever you have a new message that comes in that you need to stall. So say your protocol can't deal with that message currently. These are two functions that you can use to try to increase the performance of your protocol by either recycling the message and putting it on the tail of the message buffer, or moving it off into a different SRAM buffer to process later. These are detailed on the gem5 wiki exactly what each of these functions do. Then you have your state declarations. Here you declare all the states in your state machine. A couple confusing things here. There's this access permission. This is used for functional accesses. So if you want to, say, load a file into memory in SE mode, you use functional accesses, or just want, from the perspective of the simulator, just want to get data in memory, use functional accesses. So you have to tell the system whether or not the data in the cache is, what permission that data has. Functional accesses don't always work in Ruby, but this has some support for them. And then throughout this, we use the same notation as what they used in the Cache Coherence book, where you read this state as you were an invalid state, you're transitioning to a shared state, but you're waiting for the data before you can transition into that stable state. Next is the events. These are different events that you might want to trigger based on incoming messages. So things like loads and stores from the cache for an L1 replacements, etc. There are a lot of other structures that end up in here too. And specifically, one of them that causes a lot of confusion are TBEs. So TBEs, maybe you should ask Dan Soren exactly what TBE is supposed to stand for. There's 4 or 5 different things that you can find in the literature. But it's basically kind of like NMSHR, where you kind of use it every time you have a miss, but you also allocate TBEs some other times too. Basically, it's there to hold data whenever you're in a transient state. And so you add extra things to these TBEs, like in the MSI protocol, you store the number of acts you're waiting for from other caches in the TBE, not in the main cache. So then we get into the real meat of how we're defining our protocol. Once we've defined all these auxiliary things, the real meat of it. And that starts with these import declarations. And this is where we come to one of the really weird things in SLICC. For the most part, SLICC code looks a lot like C++. But it has a few things that are pretty weird, like peek. So peek is a function that you're calling on a message buffer, basically. So the message buffer in this case is forward n. But you actually pass it a code block. And inside this code block, you have this magic variable in message, which you can access. And so you see here we have inMessage.address. It's just magically there inside this code block. And that is whatever is at the head of this message buffer. And then the first big part of the protocol is you can trigger events based on these things. So the import is where all your logic is to decide which kinds of events to trigger. Once you call trigger, it looks through your transition list for whatever current state you are in, what event you are, and then triggers that transition. It takes these 3 parameters, the address, the cache entry, and the TBE, and we'll see why it takes these parameters next. So in your triggering transitions, you're going to be executing actions. So inside this action, you have 3 magic variables again. You have the address, the cache entry, and the TBE. So whatever data you pass into that trigger function just automatically appears when you're executing the action. So all the actions that are executed after that trigger have the same address, cache entry, and TBE. It's a little bit more complicated than that, and I talk about it more in the book. And then in Q is another one of these weird function-like things that you're actually passing a whole code block to. It's kind of like peek, but instead of populating in message, you have this out message variable, which is just automatically there. And that out message is whatever is going to be passed into the network at the end of the in queue. Then finally, you have probably the most important part, and honestly the easiest part of your protocol, which is the transitions. So for instance, this is transitioning. If you're in the state invalid and you get a store event, then transition to the state IMAD, so going to modified, waiting for both acts and data. And then perform these 4 actions. So each action is like one thing that you do, and it always does that one thing precisely. And if you need to, say, have an if condition in an action, that probably means you should have had 2 events and have 2 different events and 2 different transitions. The syntax can actually get pretty complicated to try to make these transition lists shorter. For instance, you can have, if you're in either one of these states and either one of these events happen, then perform these actions and go to a modified state. Okay, so this was a very, very brief overview of what a state machine file looks like. Things are a little bit different when you're doing directories or other kinds of caches as well. And there's a complete example of this MSI cache in the book at this address. Oh, okay. So now that you have a complete implementation of your cache controllers, the next step is to configure the gem5 system so you can use it. Now, sadly, the Ruby configuration scripts really don't follow the same style as all the other configuration scripts in gem5 at all, and they require lots and lots of boilerplate. So usually what people do is just copy all the code, paste it in a new file, and then change the few things they need to change. But that's not absolutely necessary. We can write our own config scripts. In the book is an example of writing a config script for Ruby from scratch, and we'll look at a couple of the important parts here. So when you're creating these config scripts, Ruby, you really need to do three things. You have to instantiate all those controllers that you created. And again, the state machines are just sim objects, so you can pass in parameters, just like you do with other sim objects. Create sequencers for each CPU, and we'll look at what a sequencer is in a minute, but this is the interface between gem5 and Ruby. And then you have to create the network and connect all the network routers together, which Tushar will talk more about that later. And just to briefly talk about how you create this network, in gem5 right now, it's really hidden in this function, create topologies, which no one knows what happens inside of it, and you really don't want to dig into that code. But the problem with this, and a major pain point, is that create topology assumes a specific order that all the controllers were created in. This is partly because some of the older protocols had particularly complicated topologies, like one of them is called mesh dir corners. So the idea was to have a mesh topology and directories in the corners. But this assumed that you created directory, cache, 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 directory, cache, 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 or whatever the order needed to be to get your directories in the corners. So you can't always use these topologies with whatever new protocol you create. For instance, if you're creating a heterogeneous protocol where you have different kinds of L1 caches, like say CPU, GPU caches, you really can't use any of these topology functions. So let me quickly show you what you would do if you wanted to create your own new cache topology. So here's an example of a point-to-point. So it doesn't have to be complicated. So in this case, we create routers. We're creating a router per controller, since each controller is going to talk to all the other controllers. You have external links that link a controller into the network. And then you have internal links that link routers to routers. And so in this case, we have for every router connected to every other router. So these topologies can be pretty simple. And if you have something that's particularly complicated, like these heterogeneous systems, you probably actually want to mix in this topology code as you're creating the controllers in your main simulation or main configuration file. And again, there's a more detailed example online. Okay, so how do we interface between Ruby and the rest of the system? So the interface between Ruby is just these classic ports, just like the rest of gem5. Starting on the memory side, the way this works is any of those controllers in Ruby can have a master port to send requests. And from within the state machine file, within SLICC, you can call a special function, quMemoryRead which will take an address and data and send it across this port. And then responses from the other side of the port are on a special message buffer called response from memory. So as I'll briefly say, another problem in Ruby and SLICC is there's a lot of things which are hard-coded to particular values, such as quMemoryRead and response from memory. These are just what you have to call them. But this is pretty configurable now, and recently it was updated to be able to have multiple DRAM controllers and addresses split between these different DRAM controllers. Now on the other side is sequencers. Sequencers are what converts normal packets into Ruby requests. Confusingly, there's actually two names for these, both Ruby port and sequencers. I'm going to call them sequencers. They're mostly sequencers. Really, this sequencer just sits between the port and Ruby. It is just a mem object that has a slave port, and so you can send any requests you want to the sequencer, and you don't have to have a CPU behind it. You could, in theory, have anything you wanted on the other side. It converts these packets into Ruby requests, which again show up on this magic buffer called the mandatory queue. And so this mandatory queue is what's in your L1 cache, which is accepting requests from the CPU. There's some caveats here, especially if you're trying to get a high-performance out-of-order core. If you have single cycle, if you want a single cycle hit time, you need to do some special things to get this to work, since it's a multi-step process. Okay, I'm going to skip over a couple of these things. One thing to mention about SLICC. So the compiler is implemented in gem5. You can find all the compiler code. It's written in Python. And it's important to not be afraid to dig into this compiler. If you're writing a new coherence protocol that's at all different from a regular coherence protocol, you're probably going to have to dig into the compiler. So for instance, I was doing some stuff based on region coherence. We had to dig into the compiler and change the compiler to let SLICC understand these region things. Okay, so I want to briefly mention some of the current protocols in gem5. So I went through a list of all the protocols that are in source mem protocols, and this is what we currently have. So the first few are GPU protocols, which are CPU-GPU protocols that AMD has released, some of which are relatively realistic. Then there's a couple of different messy protocols. The 2-level is private L1s and one shared L2. If you wanted a 3-level protocol that had a private L1, L2, and then shared L3, you can use messy 3-level. Just know that it's an L0 instead of L1. It starts counting from 0 for some reason. Don't ever use mi-example. That's the default program, or the default protocol. Most of the times you compile gem5, you're compiling mi-example, but don't use it. It's a terrible protocol. It's just there for an example. A few other older protocols based on older AMD chips. And then very soon, there will be an MSI protocol directly from that coherence book. There are a lot of things I didn't cover. Importantly, I didn't cover debugging, which is really difficult. But just to give you a quick hint, there's this thing called the Ruby random tester, which is great for debugging protocols because it makes sure all the controllers are actually issuing requests for the same cache line. And so it allows you to get into these transient states that normal applications might not get into the transient states. And then protocol trace actually gives you a complete trace of every single transition of the protocol, which is helpful for debugging as well. Okay, so there are a lot more details in the book. 30 minutes is not nearly enough time to talk about how to write a coherence protocol. And as you're going through, if you look at this book and you find a mistake, which I'm sure you will, because I wrote this section over the past couple days, send me an email, let me know, or if you're really awesome, you can just fix it for me and send me a pull request on GitHub. So with that, here are some more resources to learn about Ruby, and I would be happy to take a quick question. Cool. Well, thank you very much.